Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. Now, what you're about to see is a pre-recorded training session we did over in the United States. But be assured that a lot of the material that we cover is really applicable to any automotive application. So just be aware that yes, it is a lot of North American vehicles, but a lot of the same principles apply over in the UK as well. Now, if you have any questions, if you're watching this during the premiere, you can just leave it in the chat. We'll be monitoring that. And if you're watching this after the premiere, then just feel free to leave a comment underneath the video, and we'll get to those as we can as well. So my name is Jason Gabrenas. I'm one of Snap-on Diagnostics technical trainers. I've been in the training department since 2013, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple years as a diagnostic sales rep at Snap-on, so I had a group of about 30 different franchisees I worked with, as well as the shops that they service, in order to help everyone get the most out of their diagnostic needs. Then before I did that, it was 8 years at Subaru, so I worked in a dealership, and over time, I guess, I just became that default diag guy in the shop. So I always ended up having the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that had come into my bay. Then before that, a bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. All right, so our topic at hand today is diesel emission systems operations and testing. So we're going to focus mainly on the lighter duty side of things, class 1 through class 3 probably. Um, I'm sure the heavier duty side of things, like big rigs and things like that, it's pretty similar in how it operates. But we're just going to focus on, our main market segment here, which is, general repair and not really heavy duty diesel technicians, but I'm sure the principles can cross, right? So with that, let me just advance the slide here. So there's a couple different ways that manufacturers control diesel emissions. So one of the ways is in the combustion chamber itself. As the combustion is happening, based on the chamber design, the fuel atomization that happens, different ways that they have to do that with swirl and things like that. Injection timing, changing the timing. They retard the timing to reduce NOx and advance it to reduce soot. So you kind of have to go find a little sweet spot in there. They can add the EGR system to reduce NOx and more closely control boost pressure to reduce soot on acceleration. And that's a variable geometry turbo that would do that. Plus maintaining engine temperature in certain ranges and also messing with the compression ratio, making sure that's not in a bad spot where it's going to increase more emissions as well, and more. Once I've had the combustion event occur, though, I need to be able to try and control it coming out the tailpipe as well. So post-combustion, they use an oxidation catalyst, a diesel particulate filter, and a selective catalyst reduction system, which has way more components than that. We're going to talk about that as we go through this presentation. It looks something like this. This is just on an example vehicle here. We have our variable geometry turbo right here, which can kind of change and move things through the EGR cooler, and there's different valves here, and then there's a dosing injector here for the DPF. There's a pressure sensor here, pressure differential sensor right here. Various temperature sensors, NOx sensors, other temperature sensors, injector for the diesel exhaust fluid that goes in there. DEF lines could be heated. Engine coolant lines might heat the tank, or it might be electrically heated. Supply modules, filters, tanks. You need to have a place to keep it all, level sensor, etc. So there's a lot of different parts when it comes to these diesel emission systems that kind of all need to work together. So diesel EGR, that's the first closest to the front we're going to talk about. Slows combustion to keep NOx from being generated. NOx is oxides of nitrogen, so those are generally bad being released in the atmosphere. It's something along the lines, if I remember growing up in the 80s, they used to talk about acid rain all the time. Right? We'd get acid rain come over, and it'd ruin the paint on your cars and all that, and that's because the oxides of nitrogens would be getting into the atmosphere. So slowing combustion allows for more advanced injection timing, which allows to reduce the NOx, but also as a what do I want to say? As a effect of that, it's going to increase the amount of soot. So it requires the use of EGR coolers, and any diesel with an EGR is going to also have a throttle plate. Uses variable geometry turbos to raise exhaust back pressure and makes exhaust flow in the intake under low boost, which also, due to this larger amount of soot in the exhaust now, can clog up those EGR valves. So there's a clean one and there's a not so clean one. And if we look inside, that is all crudded up. Now you may be able to clean it, I suppose. Get in there real good with a brush and clean it all out, but it might still never get clean enough. So I suppose it's something you could do, but more than likely this vehicle is probably just going to get a new one, right? So once the combustion process happens, because the EGR is kind of involved in that, right? Now we have to treat it after. So common uses of that for soot anyways, we're going to start with soot and then we'll go to our NOx reduction. But for soot after treatment, we use an oxidation catalyst, a diesel particulate filter, multiple exhaust temp sensors, DPF back pressure sensor or a DPF differential pressure sensor, and a hydrocarbon dosing valve to make it all work. So the diesel oxidation catalyst is going to convert hydrocarbons into other things that are not as bad. It oxidizes dosed fuel during active regens, also increases the temperature and lights that fuel off, converts oxides of nitrogen to nitrogen gas, used during passive DPF regeneration as well. So inside a diesel particulate filter, we have some little elves or gnomes or something, and they're going to catch all the soot, and they're going to capture the soot, and then once it gets to a certain point, we got to clear the soot out, so we got to burn the soot, right? So that's basically what happens. It catches it, captures it, and then it burns it off at a different place. Right? I always say this is a very interesting thought process here because you're just carrying all the soot around and collecting it until you later go burn it off in one place. But beyond me, I'm not an engineer. Anyways, the substrate on a diesel particulate filter, it has these every other kind of checkerboard look to it. So the ones in white here are blocked off, and the ones in black are the ones where the soot would actually go in. So the soot comes into an open one, and then the soot gets scraped off by the substrate here, and then whatever's left of the exhaust gases go out through the blocked areas of the substrate. So it kind of goes through top and bottom, just filters its way through. However, if we let it go too long without getting rid of the soot, called a regen, it could end up looking like this. And this one's way too clogged. You can see all the soot coming out the front. It's just that's pretty much toast. It is way too clogged. This vehicle probably went into D-rate way before this happened, but we know how customers can be. They ignore their lights and they ignore the bells and whistles on the car. So this would more than likely need to either be replaced or rebuilt. There are places that rebuild them, but either or, I don't think a regen's going to even be able to happen on this one because once it gets to a certain threshold, it's going to say, no, sorry, not going to happen. So in order to clean them, though, before they get to that way that looked, we have different ways of doing a regen, they call it. And some manufacturers call them different words, but basically what we're doing is we're burning the soot off and putting it back in the atmosphere. So a passive regen's when the DPF temperatures are high enough to burn the soot from the DPF without needing extra fuel. This only happens under high load situations, probably towing, going up an incline, that sort of thing. Active regen can be initiated by the PCM or by a scan tool. Extra fuel is added to the exhaust to raise the DPF temps to approximately 1,025 degrees Fahrenheit. Or there's a parked regen, which can be initiated by a dashboard switch or a scan tool. It's used when attempts at active regens fail. So once you get to this point, this is kind of your last-ditch effort, and if that doesn't work, probably going to need to replace it. Active regen should be going on under normal vehicle driving down the road, right? Also, if it gets too hot, could melt. So we can see that's clearly the direction of the flow, and it melted down this thing. Or in other circumstances, it might break. So you can see all the substrates cracked and broken and pieces just sitting in there. And that's definitely not going to do its job either. So a couple different failure points on those DPFs. We want to make sure we keep them clean and tidy. Now, to monitor the process going throughout the whole exhaust system, we have exhaust gas temperature sensors. This allows the PCM to measure exhaust temperatures at various locations, in front of the DPF, behind the DPF, in front of the cap, behind the cap, all throughout the process. So it knows based on what the temperature is, whether certain things are happening, whether or not the cat lit off the fuel to burn out or regen the DPF, whether or not the regen's actually happening, whether or not the regen's complete, because it can just measure the different exhaust gas temperatures along the way. We also have a DPF differential pressure sensor. So this is going to have two tubes, and one's going to go to the front, one's going to go to the back of the DPF, and it's going to measure the pressure difference between the front and the rear to know whether it's clogged and to know whether or not a regen is needed and whether or not a regen is done. Because I would imagine once the pressures are pretty similar front to back, that means it's flowing fine and all the soot is gone. So uses that as an input. And then also to increase the temperature, as we said, it dumps fuel into the exhaust and lights that off with the diesel oxidation catalyst. So this actually sprays diesel fuel into the exhaust to heat up that catalyst, to heat up the exhaust temperatures to blow out the soot. It's plumbed to a diesel fuel line, adds fuel to the exhaust, like I said. So in order for the PCM to determine what the vehicle needs for whether or not it needs a regen, we have the differential pressure sensor. Like I said, it's going to be a pressure difference between the front and the rear, depending on how clogged it is. If present, a wideband oxygen sensor will be used, distance traveled, engine speed, engine load, air mass, engine temps, exhaust gas temps. So it can estimate the soot load of the DPF based on all of this. How far has it traveled? What's the speed? What's the load? Whether or not how much oxygen has been in the exhaust and so on. So it uses that to calculate it. Now we can see there's a lot of different sensors and components of this, and oftentimes they're in kind of a fairly compact area, but we have our NOx sensor here, before and after the SCR, which we're going to talk about in a little bit. There's the hydrocarbon injector that injects the diesel fuel before the cat. The cat then heats up and lights off the DPF. Now, some vehicles have the SCR first. Some vehicles have the DPF first. It just depends on the manufacturer's preference. We have 1, 2, 3, 4 EGTs. That's the exhaust gas temperature sensors to measure and see how things are going. And we have our diesel oxidation catalyst, our selective catalyst reduction, and our diesel particulate filter. And then we have all the diesel exhaust fluid and injectors and accoutrements that go along with that we'll talk about more in a minute. So as I said, exhaust gas temperature sensors are very necessary for this. So there has to be a minimum of 2, one in front of the DPF and one in the back of it to know whether or not it's actually lit. But many manufacturers use 3. So first one's going to be here, T1. So that is between the turbo and the diesel oxidation catalyst. That's going to be used for comparison to the outlet, which is over here, to see whether or not the DLC lights. And then we have between here, like I said, whether or not it lights. And then it's also used a comparison to the DPF outlet to see if it's burning soot. And then we have the DPF outlet to tell us whether or not it got hot or not during the regen. Also to know when the regen is over, all the soot is burned, the temperature will drop off. So we would be able to see all of that just by looking at those exhaust temperatures. And if you know what to look for in the data, you can see that as well. But that's what the computer uses in order to do that. Now, as far as SCR, we mentioned that a couple times already, but SCR stands for selective catalyst reduction. And that comes with the catalyst itself. Oftentimes a decomposition tube, but not 100% necessarily. DEF injector, which is a diesel exhaust fluid. DEF pump, tank, and lines. NOx sensors for sensing oxides of nitrogen. And an ammonia sensor sometimes, not always. And we'll talk about why that's important. One of the reasons it's important is because inside the SCR, the selective catalyst reduction system, it introduces ammonia in the form of urea in the system that combines with NOx at temperature, which is oxides of nitrogen, NO3, NO4, whatever. And then it ends up splitting that out into nitrogen and water. So both components of our air as it is already. So it takes the bad stuff and splits it in and not so bad stuff. And that is just kind of your quick chemistry lesson of the day. Now, ammonia comes from urea, and urea is basically urine, right? Most times it's man-made urea. But by burning it, we're going to have the ammonia in there, and that could cause some issues a little bit down the road. So here's an example of a after-treatment system on a Cummins. So we have the DEF dosing valve in here, so that's just going to be it's going to spray the DEF fluid into here. And then we have our SCR catalyst and a slip catalyst. Now, DEF fluid should be called diesel exhaust fluid because that's the generic term of it. A lot of folks, especially I know over in Europe and things that, over there, they have, they call it AdBlue a lot because one of the name brands of this fluid is AdBlue, and they were one of the first ones. So over here in the States, we have what's called blue DEF, and we have a couple other ones that are, they use the name blue because I guess the blue part just stuck. But AdBlue is a trademark, service mark, what have you, of a certain company that produces the fluid over in Europe first. So that's kind of why I think that's why they call it AdBlue more over there than they do over here. And that's going to come into play in a little bit too when we go live on the tool. But there's your injector. It's going to spray it into that tube, and then it's going to cause swirl, and it's going to send it off into that catalyst and do its thing. Now, as far as DEF plumbing, so tank, lines, pump, coolant heater, electric heater, level sensors, whatever else might be necessary in this tank. Now, I know you can see it in the stores all the time. They have it in the gallons, the little gallon boxes or whatever. They even at like Home Depot, they have them. But if you're in certain areas, you may even have it at the pump. I know down the street, the gas station that's down the street has it just right in the pump. So you got a diesel pump there, and you got a DEF pump over here, and you can just fill up the truck both in the blue cap. Now, NOx sensors are what is going to tell the computer whether or not this is actually working. So it's going to determine the inlet and outlet NOx readings and can be used at open or closed loop systems, but oftentimes, or it can accidentally mis-ID ammonia with NOx. So it's not necessarily the most reliable system, which is why some manufacturers, not all manufacturers, but some manufacturers use an ammonia sensor. So NH3 is ammonia. Measure ammonia levels over the after the SCR to make sure we have none coming out. Allows much greater NOx regulation because it's not going to misidentify it, and is also immune to other exhaust gases. So it's not going to misidentify NOx or carbon monoxide or any of those gases as NOx or ammonia, right? So it's not going to misidentify it like the NOx sensor does. So the operation, we have our inlet, we have our spray, and we have our outlet. This is the diesel oxidation catalyst we talked about before. That's before the DPF. Then we have our DPF. Then we have our urea injector, our diesel exhaust fluid injector. Goes through the substrate there. Goes into the SCR. And then we have another slip catalyst back here at the end to catch whatever's left. And then we have our outlet NOx sensor. So in order to do this accurately, like I said, we can try and rely on scan data with it, but if the NOx sensor gets tricked, we might get tricked. So a real good thing to do, or a real strong suggestion, would be to take your scan tool, which is going to be a lot of help with the data and everything, but then combine it with either a 5-gas analyzer, or we actually just came out in the past year with a NOx-only analyzer specifically for this purpose. So under warm-up, with the injector off, it's not doing anything. So we should see on the inlet 300 parts per million, say, at idle. That can vary, so that's not like a known good value. But let's say we got 300 parts per million of NOx coming in. Nothing's happening to make it change. There's no chemical reaction going on. So NOx out should also be 300 parts per million on the NOx sensor too. And then we should measure with the 5-gas 300 parts per million as well. The 5-gas or the 1-gas should be a check on this NOx sensor here. Right? Under normal operation, we got 300 in, we got 30 out. And then we can double check it with the 5-gas there and measure 30 out. So that checks it, right? So when the injector's on, it injects the urea, combines with the oxides of nitrogen, and then very little comes out. So it's like 10% of that, dropped it by 90%. Total SCR failure is going to be NOx in at 300 parts per million. That doesn't change. The injector's on, spraying the urea. And the outlet is going to say, hey, I got 600 parts per million. Because now I got double coming out. This thing's got a problem. Well, the problem isn't necessarily that it's got 600 parts per million. It's that it's not doing anything. So by double checking this, we can see that the NOx measured, actual NOx coming out the tailpipe is 300 parts per million. So if we know we got 300 in, we got 300 out. It ain't working. It's just spraying. And all that stuff's coming out the back, and it's misidentifying the urea as other NOx as well. So like we said, there is a fatal design flaw in the NOx sensors. So don't get fooled if that happens. Due to their design, typical NOx sensors not only read oxides and nitrogen, they can also monitor ammonia, which can give false elevated NOx parts per million readings. So we can see right there, that's data off the scan tool. When the injector went off, and with a bad cat, It was showing way higher than it should have been. And then a partial SCI failure is going to be, well, we got 300 in, according to the sensor. We got 300 out, according to the sensor. So according to that, it's not working. But if we double check it against the gas analyzer, we can see we got 150 parts per million. So it's kind of working, but it's not fully working. So there is a partial failure in the system at that point. So we can see normal, partial, complete failure. True taillet pipe knocks gives us faster fault diagnosis. We could read it with the data, but to double check and verify, verification is very important. It's going to tell us whether or not we have a problem. So here's the Blue Point branded one that only measures knocks. That's all it does. It measures knocks specifically for this case in testing diesel emission systems. Came out like a little over a year ago. One of our industrial guys came up with the idea, brought it to the company, and they said, yeah, it's a pretty good idea, good use case. So he worked its way, shepherded it through, brought it to market. So I was at a conference one time, and the company that makes those for us was there, and he was talking to the franchisees about it. And he had this nice chart here. So this is kind of just a visual of what I showed you earlier, where if we got 400 in and we got 40 out, that means we're good, nothing wrong. And if the analyzer double checks and it says it's correct. We got 400 in and we got 800 out according to the sensor, but we double check it with the analyzer and we got 400, that means it's not working. Totally failed. 150 in, 300 out, reading 300 out, that means knock sensor 1 has failed, low. 600 parts per million in, 400 parts per million reading out. Actually reading 10 parts per million out, knock sensor 2 has failed high. Because it's feasible we could have 600 coming in, but only 400 coming out, it's reading wrong, right? It's maybe misidentifying that ammonia. 400 in, 400 out, verifying 400, then that's a DEF issue. The DEF's just not doing anything. It's just, even if it's spraying in, maybe it's empty even. No DEF injection or contaminated DEF. And then if we got 400 in, 400 out, and I'm reading 250, then it's a partially failed cat because it's, once again, misidentifying that. But I just think that's a pretty useful chart. Your mileage may vary, guide only. These aren't necessarily known good values, but just know if it's way higher at the beginning and way lower at the end, that's what it's supposed to do. But if it's way higher at the end versus the beginning, that's not feasibly possible to make more oxides of nitrogen. It's reading the ammonia. That's what it's doing. So just be aware. Those are some possibilities. All right, let's go on the tool, take a look, and see what we might be able to see with some options here. So I got 4 different vehicles. First one, we'll do a Mercedes Sprinter with the diesel. This one has a couple things in it we want to talk about. So on some diesel vehicles in our scan tools, we may have an engine-related systems and controls for diesel section. So it's not necessarily going to be up under the engine section. It's going to be down here. And on Mercedes vehicles, they call it the AdBlue system. Like I said, that is a brand name. That is not what it is, but that's just what, over in Europe, that's what a lot of people call it. So it's known over there as an AdBlue system. Over here, not as much, but you still might hear it referenced. But on a Mercedes, it is under this section right here for selective catalyst reduction. So anything servicing for this or what have you, it's going to be in here. So codes, data, functional tests. We go into special functions. We can see resetting the calculated fill level for the tank, AdBlue return, visual leak test, dynamic test of the delivery pump. So there's a few different tests that you can do in there. If we look at data, fill level, AdBlue temperature, temperature values, test values while driving. AdBlue metering, so there's a bunch of stuff in there. Got to stop communication. Got to do a key cycle on every Mercedes or you're going to break it. All right. The rest of the stuff, though, not the SCR stuff, but there's some SCR stuff in here too, I believe. But if we go into engine, it's going to be under functional tests, special functions. So we do have injector programming in here too. I didn't really mention anything about injector programming, but on many diesels, especially direct injection ones, you're going to need to get a code off the injector when you replace it. It's not necessarily emissions, but I guess it is kind of related to emissions because that's where it all starts, right? So replacing an injector is essential to save the QR code of the new injector to the engine control unit. It's going to be 7 characters on the top of the relevant injector. Then you're going to find the injector you want to change. You're going to hit edit. You're going to type it in. You're going to hit OK. And then it'll be set up for the proper injector flow. All the main functions are going to be under adaptations. So teach your pressure regulating valve, DPF pressure sensor, teach and use DPF, replace DPF. Let's see, regen of the DPF while driving, reset learn values for AdBlue metering, teach in process after replacement of the SCR, teach in process after replacement of temp sensor, upstream of the SCR, NOx sensor relearn values when you replace the NOx sensors on these, even if it's just one. You have to give it a teach-in process, so it's going to go in. It basically just resets values to factory. It's going to take a few seconds here to do that, and then it's going to give me a 10-second countdown when it's ready. There we go. Here's my 10-second countdown. All right, there we go. Done. All right, replace DPF, like I said, teaching throttle valve stops, zero quantity calibrations. Oxidation catalytic converter, so all sorts of different things in there that can be done related to the diesel emissions. And if we come in here, EGR actuator there, and then we also have cylinder deactivation to check for misfires. So all good stuff there. So that's Mercedes. Let's go to a big old F350 here. Now a lot of Fords are going to be pretty much the same, whether it's a V8 or a 4-cylinder diesel. In this case, we do not have extra stuff down here. So it is all under the engine. So if we go into engine, functional tests, special functions, and then we have dynamic regen where it's driving down the road, static regen where it's standing still. There's that fuel injector correction factors is what they call it there. Other Fords call it injector quantity adjustment, depends on the year. Selective catalyst reductions, all that stuff's in there. So dosing measurement, system emptying, refilling, activation, visual leak check, all that's under a separate heading. Fuel injection correction, I already said that. It's static regen. So this procedure will command a DPF regen. A manual DPF regeneration may take up to an hour. For static regen, the test will increase the engine speed to high RPM for an extended period of time. For dynamic, you'll have to drive it. So I chose static. Always perform the DPF manual regen procedure outside the exhaust system. Adjacent components and exhaust outlet temperatures are very hot during this procedure, like we said, over 1,000 degrees Fahrenheit, which increases the risk of personal injury. Keep people and combustible materials away from the hot exhaust system. And make sure you're okay. Hit yes, and then it's going to run. Right now, in this case, it's going to say it can't run because my simulator's throwing some wacky numbers at it. So it said it's going to measure the soot load. Remember how I said it can kind of guess what the soot load is? Of 771% in this case. 50 to 99% is partial. 100 to 120 is fully. 121 to 199 is overloaded, and above 200 is clogged. So it is not going to let you go past this if it's over. If it's probably even in the overloaded sections, going to be questionable whether it'll let you do it. Above 200%, it's probably not going to let you do it at all. So in that case, percentage of soot load is higher than the maximum limit to perform the DPF regeneration. To prevent dangerous overheating of the diesel particulate filter, and DPF regen has been disabled. So once it gets over a certain threshold, it's not going to let you do it. Now, I know some Dodge vehicles like Rams, they have a problem with that where they'll even set a code. If a customer drives that vehicle long enough where it gets to the point where it's that loaded, they ignored a lot of warnings by the time it got to that point. Warnings and D-rates and all sorts of stuff. So it's kind of their fault that they're in that situation, but there's nothing you're going to be able to do to regen it. They're like, oh, why can't I regen this truck? Well, it's got this code in it, and that means it's clogged. So also on some vehicles, this Ford included, if you have a tool with guided component test, it's going to have guided component test information in here as well. It's even got a section for diesel emission control under the engine. And there's a DPF differential pressure sensor. All right, so we got some information on that. Let's see, EGR system, exhaust gas temperature sensor, exhaust pressure sensor, glow plugs, which is not necessarily emissions, but let's see, particulate matter sensor, particulate filter pressure sensor, reductant injector, reductant pressure line, reductant pump, reductant control module, reductant quality module. So all of those things, turbocharger actuator, that's all related to emissions on diesel. So a lot of good stuff in there. All right, let's go with a GM. It's going to be similar but different. So on the GM here, we have glow plug control and power takeoff control under our additional engine-related systems. So that means everything's in here. Functional tests, DPF tests, reductant system, service bay test, reductant system tamper warning test. So DPF tests, regen enable, service regen, pressure sensor reset, catalyst reset. Cylinder balance, power balance. No, that's never mind. Output controls. That's what I wanted to look. So catalyst reductant loading reset, NOx catalyst reset, NOx sensor reset. Once again, 1 and 2. Reductant heaters, fluid tank levels, reductant injectors. All sorts of emission stuff in here under output controls as well. And I didn't check this one last time. Let's see if there's got a component test for this. There should be, I would think. Oh, they only have the gas one. That's interesting. All right. How about this one? There we go. 6.6 diesel. Engine. So we got, let's see, diesel emission control there. So DEF injector, DEF purge solenoid, and the hydrocarbon injector. We got information on for that. Coolant temp, exhaust temp sensor, exhaust pressure sensor. So we have a few in here. Not as many as the Ford, but maybe not quite as complex. And lastly, we'll pick this little Jeep Renegade here, a little 4-cylinder. That's a 22, so it's got security link. Okay, so let's see. Engine-related systems, we have a dosing control unit here. Now, there's no functional test, but we get codes and data. Might need that. Means everything else is under engine. We got functional tests. This is going to be mainly your lamps. All right. Turbocharger pressure actuator, though, it can move backwards and forwards. System tests. EGR high pressure valve test, EGR low pressure valve test, VGT actuator test. That's pretty much it for emissions. And then we'll go to miscellaneous functions. So let's see, DPF sensor replacement, EGR high pressure valve replacement, low pressure valve replacement, electrical VGT sensor or turbo replacement, injector replacement. Once again, you got a code injectors here. Let's see, particulate filter replacement, particulate filter regen, NOx replacement. So a lot of different things that you might need in the scan tool for that. So it's across the board, really. Our diesel coverage in our scan tools is very solid, including some guided component information depending on what type of vehicle you're on. So that is diesel emissions. Hopefully you got a couple little tips out of that. And with that, that's our time here today. So make sure you tune in for new diagnostic content every week. We'll be premiering a new video every Wednesday at 7 p.m. UK time, so make sure to check it out here on our YouTube channel. Please make sure you also subscribe, thumbs up, and ring that little notification bell so you'll know anytime we post new content. With that, time for questions. Now, if you have any questions, once again, if you're watching this on the premiere, just leave it in the live chat and we'll do our best to answer those. Otherwise, leave a comment under the video and we'll get to those as we monitor those comments as well. So I'd like to thank you for taking a little bit of time out of your day to learning a little bit more about how you might be able to be more efficient at diagnosing vehicles using some of the information that we've been giving you today. Hopefully we'll see you next week, and we'll see you on any of our other videos. Have a good week, have a good night, and take care.